and, and you have to write down your name before tomorrow at
os dois falam
midday.
junto?
There's a list up there, and the t-shirts
Eu
will get here
vou.
on Thursday.
Tô os
Ok?
dois falando junto. Raul, agora sou eu. Testando.
Okay. Then let me introduce the next speaker, Professor Mjsaia from ICMC, who is going to talk on from Mignon number to Bush boundary multiplicity via Newton polyeder.
Alô? Tá escutando? Tá. First, I would like to thank you twice, the organizing committee. My first thank you for the organizing committee is that because they are organizing this workshop. And for the first time in 12 years, I can follow the talks of the workshop, at least from the beginning. And now I want to thank you for the invitation to give this talk. It's a great honor for me to be here. And I want to say happy birthday to Professor Mjsaia. It's a great honor for us to receive you and to celebrate it here, as we said before. And now I am going to, before starting my talk, I'd like to say that I am very happy to see that we could call this day of Newton Polyhedra Day. Because all the talks that were given in this day, including the talk of Professor Terry, are talking already about Newton polyhedra. So it's very nice for me to give this talk in this. And I changed the name of the talk just to say a little bit about the history of the use of Newton polyhedra to compute numbers. Already to count everything that you want, you can use Newton polyhedra. The first number that I want to talk, as I am giving a talk in a singularity theory workshop, this is the most famous number that I know, and I'm sure that you heard about it all the time. It's the Milnor number of isolated singularity germ of function, complex germ. And there are several geometric interpretations. I prefer to talk about the number of Morse points in a stable deformation of the germ. If it has isolated singularity, we can compute a stable deformation to compute this guy. And the algebraic formulation for this number was given as the complex dimension of the ring ON of the germs of functions, quotient the gradient ideal of the germ. This is the first number which I want to talk. There are others, which are generalizations of the Milnor number, and they are very well known in singularity theory. And the first guy that I say is the number of cusps. Whitney gave the first result in singularity theory, telling that any application from R2 to R2, which is stable, has only cusps and double folds in the image set. And here I am talking about the work of Gaffney and Mond, which says that the number of cusps is given by the complex dimension of this algebra. And this is the determinant of Jacobian matrix JF. But here we have some, Here we have something else, which is a 3 minors of the iterated Jacobian matrix of this guy. I will talk about this later. This is already the number of cusps which appear in stable deformation of F, and it's quite a generalization of the Milnor number. Another number which appears often is the famous number of cross caps. We say that's the Whitney umbrella. That's why I told about Whitney here. And this result is given by David Mond, and says that the number of cross caps in a stable deformation of the germ is this complex dimension. Again, we have O2. I believe that, it's okay, it's O2 also. but the quotient is over the 2 times 2 minors of the Jacobian matrix. And it's also a generalization of the number of Morse points in the germ of function. There are others which also generalize this result. One of them is the number of points which we call the CI of F. This is a work that I developed with Ballesteros a long time ago. And we realized that we could find the generalizations of that guys that I told before using the image of points of Tom Boardman singularities for a Boardman number. And we need just to know if the iterated Jacobian ideal is Cohen-Macaulay. If we go back to map germs from C2 to C2, this is the Jacobian ideal iterated the J11. If we go here, is the J1, or J2, if I'm not wrong with the notation. Here is quite a generalization of this guy. And we also have a way to compute this number using a complex dimension in this sense. This is a work of a long time ago, and the most important in this thing is that we are computing already Hilbert-Samuel multiplicities of ideals. And any complex dimension in this situation, we are computing some multiplicity of some ideal. So the main question to talk about the applications of commutative algebra to singularity theory is to give an answer to how to compute the Hilbert-Samuel multiplicity of an ideal. Okay? There is a full theory developed to show how to obtain the Hilbert polynomial associated with the projective resolution of the ideal. Very technical results. And very hard to already compute these guys, even for examples. If you use a computer, you can do it, but mathematically it's very hard to compute these guys. But there are some conditions that we can already compute the Hilbert-Samuel multiplicity. The first, which I want to say, is that the result of Cauchy-Nierenko. And now, we are showing how to use Newton polyhedra, at least to motivate you to understand the construction of Newton polyhedra. I will give an example in a few minutes. And Cauchy-Nierenko, in the first, I don't know if I talked about him before. No. But he gave a very interesting method to compute the Milnor number. But to compute the Milnor number, he developed the theory to compute the Hilbert-Samuel multiplicity of this ideal. Not the gradient ideal, but the ideal generated by x1, the f x1, xn, the f xn, in the same conditions that we see for the Milnor number, but a different ideal. And the result of Cauchy-Nierenko, I will talk about the Newton non-degeneracy condition a little bit later, but he computed the complex dimension of this ideal, which is already the multiplicity, Hilbert-Samuel multiplicity of this ideal, in terms of the Newton volume of the Newton polyhedron given by the germ F. And he already showed an equality if the germ is Newton non-degenerate. This is the first 1976, if I'm not yes, result that I know. And it's important to emphasize here that the result of Cauchy-Nierenko to compute the Hilbert-Samuel is to compute this guy, and from the Hilbert-Samuel multiplicity of this guy, he computes this Hilbert-Samuel multiplicity of the gradient ideal. And using products of ideals, he decomposes these guys in products of ideals and obtain the gradient ideals from the multiplicities of monomial ideals and this one. This is very important to understand the result of Cauchy-Nierenko. We have here some results which are well known in singularity theory and which are very important to compute the Milnor numbers, because they give results, on the topological triviality of families of function germs with isolated singularity at 0. So if we have the topological triviality, we have the constants of the Milnor number. So we are already computing here in all these results families with constant Milnor number. Moreover, any of these things are done using the concept of the integral closure of ideals, which was explained by us with Professor Terry. And he has a very huge work in the integral closure of ideals, and not just ideals, but other things. But I want to emphasize here the work of Yoshinaga. The work of Yoshinaga gives conditions for the topological triviality. This work of Damon Gaffney and Fukui Yoshinaga, they work already with this ideal, xi, the f, the xi. And Professor Yoshinaga showed to me for the first time the construction of the toroidal embedding. Anytime that you want to construct the integral closure, if you know how to construct the toroidal embedding associated to the Newton polyhedron, you can control the integral closure. If you can control the integral closure, you can control a lot of inequalities, any inequality that you want in the complex set. So this is very important tool to describe a result that I will talk in 2 minutes. Before I want to talk about the work of Tessier, which also gives a formula to compute the multiplicity of an ideal, but a monomial ideal, which is already given in terms of the volume of the Newton polyhedron. This work is of 1988. This is 1989. This is, I believe that's 1987. I'm not sure, a little bit before. The work, this is 89. It's here. Yes. This is a little bit before. I believe that this is a little bit before also. And this is 1988. Things done independently. But the result is very interesting because here we also compute the multiplicity, but in a general setup, but for monomial ideals. Moreover, to obtain such result, as I told before, we need to compute the integral closure because the integral closure gives the multiplicity to us. The Hilbert-Samuel multiplicity depends only on the integral closure of such ideal. And then, if we can compute the integral closure of monomial ideals, we can compute the multiplicity using Newton polyhedron. 1996, I developed this work in 1993 when I went to Liverpool. And in this paper, we did a kind of generalization of the results given before. In fact, I was really interested in the result of Yoshinaga. I'm not showing the result of him here because lack of time, but from that result, I could give a characterization of the integral closure of ideal, which is Newton non-degenerate. Using Newton polyhedra, that's the only way that we know how to compute these things. And I will just give you a short example of how to compute a Newton polyhedron. To compute, you just need a set of, considering 2 variables, a set of pairs in R2. You can compute anywhere, but you just take points in the space and take convex rules. Then you count the points which are inside these guys. Looking in the context of analytic functions, we are considering just in 2 variables case, monomials x, r, y, b. So we are in R2. We are associating these guys to the pair AB. And then we put all monomials that we want to work with them. And from these monomials, we take the convex rule, which in general for the Newton non-degenerate case, you can see something like that. So we are associating monomials to the set of exponents of the monomial and taking the convex rule. Only this, nothing else. It's interesting to remark that this is called the Newton polyhedron because Newton worked on this subject to compute zeros of polynomials, which are closely related to the singularities of the polynomials. Newton did it in the two-dimensional case, but it's the theory to develop these guys. To compute the Newton polyhedron, to use the Newton polyhedron to compute the integral closure, we need to give something in terms of the convex rule for the set. Here I'm considering any polyhedron in any ideal, okay, in the set of germs of functions, for example, analytic functions. And then I am trying to compute the integral closure of this ideal using Newton polyhedron. So we define this guy, the convex rule of all monomials, such that we have xk belonging to the integral closure, and we computed another polyhedron here as a convex rule. And then we compared these two guys using already the comparison done by Yoshinaga before, which I didn't show, but we were able to show that first the integral closure, the convex rule of the integral closure is already in the Newton polyhedron, and the equality holds if and only if the ideal is Newton non-degenerate. I'm not going to give the definition of Newton non-degeneracy here. Sorry, but I am giving to show a more general definition later when we talk with modulus. The main tool to use this is the construction done by Yoshinaga, but Yoshinaga worked just with the gradient ideal, or more specifically with the gradient or the ideal given by xi df dxi, as I told before, this ideal. He computed already the convex rule of that, the integral closure of that ideal to compute his results to give topological triviality results. And the proof for this result is given following the proof of Professor Yoshinaga. And then I realized that the toroidal embeddings are really the right guy to compute these numbers. You can use them often because you can control the integral closure of the guy that you work. And that's interesting to remark that when I wrote this paper, I didn't know the result of this year. I just met this result a few years later when Carlos Bivia showed me in 1998. It's interesting, but I generalized something that I didn't know. Carlos Bivia that showed me this sometime later. After that, we did it together with Fukui, a nice generalization of these results, giving a full characterization of a Newton non-degenerate ideals when it's generated by n guys. Okay? Since we are computing the integral closure condition, we just need to see ideals generated by n generators to be sure that we have a finite codimension. At least this is a necessary condition. Then we can consider the reduction of any ideal given with n generators and then apply these results. The multiplicities will appear. But this is a characterization of a Newton non-degenerate ideals. Any other is more complicated. But my talk today is not about this. This is just a full motivation to talk about the Bush-Bauhin multiplicity of modulus, also using Newton polyhedron. And the Bush-Bauhin multiplicity is a generalization of the Hilbert-Samuel multiplicity, and it was done by Bush-Bauhin in 1964. And moreover, we have in the work of Rees, 1987, so the same time that the other people were working in singularity theory to compute Milnor numbers and topological triviality, Rees was developing the theory of integral closure for ideals in a general setup, to modulus, sorry. And this was realized by Terry Gaffney in one of his articles. But just to give a setup, to show the construction of the Bushbound ring multiplicity, we need to consider a very strong setup in commutative algebra. I still have some difficulties to understand these things, but we have the symmetric algebra of the modular RP. And then we have the his algebra given by the direct sum of these guys. And from this, it's possible to define the Hilbert function associated to the module M, given by the length of these ideals, this quotient, sorry. And when we do this variation for n, it becomes bigger and bigger and bigger. It was shown that this is a polynomial of degree d plus p minus 1. D is the dimension of the ring R. And in this case, we have here a number which is called the Bushbound ring multiplicity of M. This is the more effective way to compute these things in terms of the projective resolution of the module of the idea or something, to compute the Hilbert function, from the Hilbert function to compute the numbers. This is the algebraic way, point of view to compute these guys. This is why we need to know a little bit about algebra, which is already not my case. But on the other side, there is a comparison of Kirby and Rees given to compute the Bushbound ring multiplicity in terms of mixed multiplicities of ideals. The mixed multiplicity of ideals is a theory developed by Mjsaia and Risley. I'm sorry if I didn't wrote Risley here. And Kirby and Rees showed how to compute the Bushbound ring multiplicity in terms of the mixed multiplicities of the ideals, which we can decompose the module of RP. We just need to have ideals of finite colength in R to conclude that M is of finite colength, and then we can compute the Bushbound ring multiplicity in terms of the mixed multiplicities of the ideals. There is a generalization of the mixed multiplicities given by Kleiman and Torup and also by Kirby and Rees, which is a generalization of the mixed multiplicities given by Mjsaia and Risley. And this was published in 1996. And the mixed multiplicities are defined the same way that we see any kind of multiplicity that we are computing. We need to compute the Hilbert function. This Hilbert function is the length of this quotient algebra. But here we have a Hilbert function in S variables because we are considering a family of submodels of finite colength in the same space RP, okay? And to compute the mixed multiplicities, we compute this length. Then we do the same procedure to take N1 and S big enough such that we have a polynomial here, not just a function. And we know the degree of this polynomial is d plus p minus 1. And then we have several numbers appearing when we have the sum d1 plus ds given d plus p minus 1. So there appear several numbers here. And these numbers were called by Kleiman and Torup the mixed multiplicities of the family of modulus M1 of M1 MS. It's interesting to remark here, they are all submodulus of the same space RP, okay? And then this is the symmetric algebra, and this is the product of the, for any HN, we have this. Then, our first question in this subject was to show that it was possible to compute the Bushbound ring multiplicity of a sum of modulus in terms of the mixed multiplicity of the family M1, MS. the same way that we see the result of Kirby and His to compute in terms of the mixed multiplicity of ideals. So, the main problem is that the only way that we know how to do it is to apply a lemma of Hermann, Hiry, and Hibby to the polynomial K of N1 and S. The polynomial is this, given to compute the mixed multiplicities, to transform it in a polynomial in one variable, and with the leading term given by the Bush-Baum-Ring multiplicity. And the main problem is that we only know this way to compute this, to go from N1, Ns variables polynomial to another polynomial with just one variable. We do a recursive method such that we eliminate one of the variables until we have all transformed in just one variable. But from this lemma, we can never do this to come from the polynomial which gives the mixed multiplicities to the polynomial which gives the Bush-Baum-Ring multiplicity, because we have a big problem with the degrees. When we apply the lemma of Hermann to this guy, we will obtain a polynomial of degree d plus ps minus 1 plus s minus 1. And we see before here the polynomial is of degree d plus p minus 1. So we have a positive answer to this question just only when s is equal to 1. And this goes back to the result of Kirby and His, which gives, in terms of a direct sum of ideals. When we realized this, we stayed at least 5 minutes, stopped and looked into the blackboard and say, oh, what can we say now about that? And 5 minutes, we nothing to say, then we decided to do something different. If this is not appropriate to give us, using the method of the recursive method given by that theorem which I told you, we need to define a new set of multiplicities to a family of submodulus to compute the Bush-Baum-Ring multiplicities in terms of this new set of multiplicities associated to this product of the sum of modulus. So we decided to give a new definition of multiplicities, which is given in this sense. We take the tensor products of for each SMI, and just a second, here we are not fixing the same RP space. We are just considering that each MI has finite colength in some RPI. And we call the direct sum, take the modulo, and we take P, the sum of these PIs. So we defined a new Hilbert function in this setup. It's always called the Hilbert function, we call it H, with S variables because we have S modulus as a length, okay? And we compute this kind of the calculation for these guys for any kind of sum E1 plus IS, which gives n plus p minus s. This is the main difference. Not n plus p minus 1, but n plus p minus s. From this, we defined a star multiplicity, which are given by the coefficients of these polynomials. Okay? If we take all great values of the variables, we get polynomials, and we get this coefficient. And to our happiness, applying recursively the result of Hermann, Hiry, and Hibby to the polynomial P star, I called it P star, the polynomial associated with this guy, which is a polynomial after some time, and it's not written here, sorry. And from this polynomial, we can go from the star multiplicities to the Bush-Brown-Hinn multiplicity, applying the I don't know how to say it, Ribbe lemma. And, of course, that if you consider M a direct sum given by ideals, we have the result of Chibbe and Riess. My purpose is not just to describe the Bush-Brown-Hinn multiplicities. There are several works that describe it, but to compute it. And again, to compute it, we're using the Newton polyhedra. In this setup, we have the works of B.V. Alzina. B.V. Alzina is doing a very interesting work using Newton polyhedra to compute a lot of things, not just Lojazevsky exponents, but other things also. And he has a very interesting article showing how to compute the Bush-Brown-Hinn multiplicity in terms of volume of Newton polyhedra. I'm going to show you later. But before it, I need to give a result of Gaffney, which is the main tool that, as I said before, to compute integral closure of modulus in terms of the integral closure. I'm sorry, but I believe that here we have some integral closure. This is overlining. I believe that I have one here. I'm sure that we have to compute the integral closure of a modulo in terms of the integral closure of the ideal generated by the minors of the matrix M for a submodulo in ONP. ONP is the set of map germs from Cn to Cp. We are considering here this setup because we have some conditions which are interesting. This is the condition given in terms of, from these results, we translate it to this condition. And these results are given by Gaffney in his paper of 1992, very interesting paper. And from this, we have some results given by Carles Beaver, which I will describe now. First, I want to fix the Newton polyhedron of the modulo M, given by the Minkowski sum of the Newton polyhedron given by the projections of this modulo in ON. So we have ideals which are given by these projections. From these projections, we have the Newton polyhedron of each one of these guys. Then we take the Minkowski sum. From this, we have some technical definitions given by Carles Beaver to give the definition of a Newton non-degenerating modulo when we have this condition, okay? And from this definition, we have some results of Beaver-Alzina also. Here he relates the integral closure of the modulo with the direct sum of the ideals given by the monomials which are the monomials of each ideal I0 of I0R of I0I they are generated by all monomials which are in this Newton polyhedron. Very interesting way to see these guys. As I showed you before, this condition in this theorem also, which I did with Carles and Fukui. I have time to here. Here we have the idea of monomials also. I didn't explain it here, but it appeared again here, but in the modulo case. But are the same monomials, okay? And moreover, we have these conditions always. We have a Newton non-degeneracy condition of the modulo M, given by definition before, if and only if the ideal generated by the P times P minors of M, of the matrix M, is Newton non-degenerate, and both Newton polyhedron, this and this, are the same. This is a technical result, this, not this. This is a very interesting result. And this condition, we can do some examples to be sure that it works, but Carles already showed it. And Moreover, he characterizes the submodule satisfying these conditions in terms of the Newton non-degeneracy. M in ONP is Newton non-degenerate if and only if M is given by the direct sum of all monomials in the Newton polyhedron of the volume of the M, modulo M. And now we did some generalization in the sense of Carles to compute the star multiplicities. We already applied the results of Carles to do it. And again, I am talking about the integral closure. I told it before, sorry, here I should put it before, but now I realize that it's in the wrong place. This is the definition of the integral closure for a module. We really need these conditions, the integral closure condition, to compute any of these things in terms of multiplicities. And for the integral closure, we can first show that the integral closure of M, if we are in these conditions, projecting these guys. So if you can take M1, MS, so we have the integral closure given by the direct sum of the integral closure for any partition, okay, of P, not just for partition given by 1, 1, 1, 1 P times in any situation. And in fact, this result is the direct consequence of the definition of star multiplicity, because this definition is given as a length, and if it is a length, it's given already by the reduction of the ideal, which it's given by the integral closure. And moreover, we followed the work of Carles Bivia to define the Newton numbers associated to the star multiplicities, and define these numbers V star I1, IS, M1, MS, such that they are described in terms of the sum of the mixed multiplicities of these guys, and we have to choose these guys in an appropriate way to define these guys. And from this definition and from the results of Carles, which we strongly use here, we define this number as the sum, and for the guys which satisfies N plus P minus S, because we are working with the star multiplicities, and these are the numbers which we fixed to define the star multiplicities. And then we showed that the star multiplicity is given by this sum. And moreover, we showed that the star multiplicity is given by this equality if the modulo is Newton non-degenerate. And for any partition of P, we define the number delta star P of N given by the sum of the star multiplicities in this condition. Then we obtain the Bush-Baum-Ring multiplicity is bigger or equal than this guy, and the equality occurs if and only if we have this condition, okay? This is the proof. I will skip this proof now. It's strongly based in the results of Kleiman, Torup, and of Carles Bivia. And then we have these propositions. The equalities occur if and only if M is Newton non-degenerate. This is bigger than this. This is bigger than this. Okay. The proof is strongly based in the result of Carles Bivia again. And then we can give this more general result, telling that M is Newton non-degenerate. This ideal is Newton non-degenerate. These results are given by Carles Bivia before, but here we have the composition of modulus M1, MS, not ideals only. We have the Bush-Baum-Ring multiplicities. We have this multiplicity given by this number, and the Newton non-degeneracy condition for all ME which appear here. Okay? And so we recover the result of Bivia in this case, and these are thank you very much.
Is there any question? Okay, if not, then let's thank the speaker again.
Socorro, como que é isso?